Yay. Okay, today is Tuesday, March 12th, and today we're looking at the quotient rule. So please turn to the quotient rule in your book. That's on page 16 of your orange book. Okay, the quotient rule, unlike the product rule, we are not going to prove this one in class. I did prove the product rule yesterday, and it sort of went over like a lead balloon. I mean, it's sort of, the students did sort of follow it, but it won't be tested. Neither of those proofs will be tested, but they are quite interesting, and there is a proof in your textbook if you'd like to read it, okay? But let's take a look at the quotient rule in its glory. You're probably wondering what this quotient rule will look like. Well, the good news is the numerator of the derivative is almost identical to that of the product rule. So that's sort of nice. We're still going to have f prime g, and we're still going to have fg prime. But a vital difference will be, we won't be adding those two terms, we'll be yes. So even though there's many ways to write the product rule, this is my favorite way of writing it, and I see your teacher uses the same way, because it lines up many with the quotient rule that way. The quotient rule has one extra thing with it. It actually has a denominator, but down there, interestingly enough, is just g squared. All right, so g squared. Now, I know that this probably doesn't make a lot of sense to most of you, but keep in mind this is g to the -1 power down here, right? And what do you do when you use the power rule and you take something with x to the -1 power and take its derivative? You get the negative, and you get it going downstairs as a square, right? So just as the derivative of x to the -1 is 1 over x squared, so it's the same thing with g. We end up with a g squared down there. Okay. Now, more officially with the Leibniz notation, or Leibniz, however you say it, if you want to take a look at putting it in this way, I'm just going to use the ddx format. So more officially, it would look like this. All right, so that's the official way of writing out the quotient rule with the complete notation. And this is an abbreviated notation here. And in words, we could do it this way. Derivative of the top, leave the bottom. Subtract, leave the top. Derivative of the bottom. All divided by the bottom squared. And some teachers have come up with jingles like, yeah, low D high minus, you know, that kind of thing. I'm not big into that, but your teacher's got it in your book there if you want to use it. All right, so this is the quotient rule. The proof, this can be proven using the product rule and the chain rule, and the chain rule is introduced in the next section. All right. All right, we're ready for our very first quotient. Okay. I'm going to make a statement, and I want you to tell me if it's true or false. Here I go. Here's the statement. All right? Don't get me laughing, please. All right. Here I go. All right. Every question that can be done with the quotient rule could have also been done with the product rule. True or false?
No.
How many think it's true? Every quotient rule question could have also been done with the product rule. True? How many say it's false? Okay. Hold it.
Yes.
There's one?
Then yes.
Yes. Yes. Okay, thank you for standing up for what you believe in. All right? Okay. Yes, yes, you're wrong this time, but at least you stood up. Okay? Now, what do I mean? And you don't actually have to write this down, but I could have written f of x like this. Right? I could write it as a product and then use the product rule. Now, some of the methods that we have learned, some of the methods that we're about to learn will make it more possible to do a question like that with the product rule. But for now, we're going to use the quotient rule. All right, so the quotient rule works like this. This is your f, that's your g. So it's quite simple. If you want the derivative of this f, unfortunately there's a multi-use of the letter f here. We also use the f to signify the first term and g to the second term. But we also use it for the function sometimes. So f prime of x. I need your undivided attention here. You don't want to miss this. All right, so stay with me. I'm going to start by taking the derivative of f. It's 1. Yes, it's 1. The derivative of x is 1. Then I just write down g. I've got an easy road now for a little while. I just write down f. Now I finally have to do another derivative, and that's the derivative of g. Can someone give me the derivative of g? 2x. If you said 2x minus 1, keep in mind the derivative of a constant is 0. So it's just 2x. Who knows what I would put on the bottom? Yeah, so x squared minus 1, quantity squared, right? The whole thing squared. So now on all of these, once again, we can simplify them somewhat. What I'm going to do is simplify the numerator here. I am not going to simplify the denominator. I'm not going to multiply that out. Okay? I'm just going to leave it there. But in the numerator, what will I get? 1x squared minus 1. And then minus 2x squared. Simplifying that even further, I get negative x squared minus 1, x squared minus 1 squared. Now, had that been a negative x squared plus 1, I could have gone one more step and reduced with the denominator. But it won't reduce, because even if I factor out the negative from the numerator, I have x squared plus 1 in the brackets, which does not divide out. So there's sort of an unwritten rule. If you're not going to gain anything by doing the simplification, you just don't do it. So I'm going to be happy just leaving it like this. That's about the only simplification I would do there. Now, question, yes? No, you could. You could factor out the, you mean the negative 1? Plus 1, which does not factor. So there's no advantage to doing it, but you wouldn't be wrong to do it. So it'd be an optional answer. Okay? All right, so number 2. This is one of those where we're working numerically instead of with variables. All right, so this time we're doing the derivative at 2. So what do I want? I want actually f g prime at 2. That's what I want. So of course, I'm going to take my derivative with 2 in mind. So what is it going to be? It's going to be f prime of 2 times g of 2 minus f of 2 multiplied by g prime of 2 all over g of 2 squared. Now, they gave you the value for all 4 of these different expressions, didn't they? Can you put them in this little fraction here and simplify it for me? Go ahead. Put them in and simplify. Your answer should be a fraction. Okay? It's a proper fraction where the numerator is quite a bit smaller than the denominator. In fact, the difference between your numerator and denominator should be 13. All right, so each one of these was given, right? So if we use that as a template and then just put in exactly what we were given, that one was given at 3. That's f prime of 2. G of 2 was given at 6. And then f of 2 was given at -4. And then g prime of 2 was given -2. On the bottom, we want g of 2, which is 6. So we have 18 minus 8 over 36, which is 10 over 36, which reduces to 5 over 18. How many are looking at that answer? 5 over 18. Okay. All right. Okay. Oh, Mr. Ashton pressed extend page. What does that mean? Will this be a hard one? Well, there are 2 steps to this question. Did you notice they're asking for the domain this time? Oh, yeah. Oh, yeah. Now, with algebraic functions like this, we have a possibility of 2 domain violations. What are they? One violation would be dividing by, and the other domain violation would be taking the square root of a negative. And unfortunately, this denominator has the potential of committing both violations. Yes. Both violations. Yeah, you heard me right. Okay, let's discuss them one at a time. First of all, we do not want x to be less than 0, right? We don't want x to be less than 0, so the x coordinates that we do want are greater than or equal to 0 as far as the square root is concerned. But the other thing we don't want is we don't want the square root of x to be equal to 3, do we? Do we? If you square both sides, then x cannot be 9. How do we put these both together? We could do interval notation. So, I'm going to do interval notation for my domain. My domain will be all x coordinates greater than 0 but less than 9. Notice 0 is okay here. 0 is fine. That's why there's a square bracket around 0. But 9 has a round bracket, meaning 9 is excluded. Unite that with what? 9 up to, and infinity always has a round bracket, always. So our domain has two parts. We could also use set builder notation to give the domain here, but this is interval notation. All right, so there's my domain. That's sort of the trickier part of this question. The rest of it's not too bad, actually. If I want the derivative of f, I will need the derivative of the top multiplied by the function as it stands in the denominator, subtract the function as it stands in the numerator, multiplied by the derivative of the denominator. Now, I've got to be careful here. Yeah, the 3, the minus 3, the derivative of that part is 0. But what's the derivative of root x? It would be 1/2 x to the negative half. Now, this is where students traditionally make mistakes, because they think this is in the denominator already, so they treat it like x to the negative half. It's not. So when you use this formula, it's like you're zeroing in on parts of it at a time. So when I zero in on the denominator and take its derivative, it's like, for a moment, it's in the numerator. Right? So just pretend it's in the numerator and take its derivative as it is. So the derivative of root x would normally be 1/2 x to the negative half. And that's what it is here. Did I lose you there? I hope not. How many understood what I just said? Okay. Now, in the denominator, I'll have root x minus 3 quantity squared. So on questions like this, we do what's called limited simplification. What do I mean by limited? Normally, we leave the denominator as it is. Okay? Most of the simplification takes place in the numerator. So we try to make our numerator as simple as possible, and then we observe if there's any possible cancellation with the denominator. If not, we just leave it. Okay, so that's the only time the denominator would get multiplied out or anything like that. All right, so let's change everything to fractional exponents here. So I'm going to write my root x here. X to the half. I should have done that on that step. Sorry about that. But I'll write it as root x to the half there. Okay. Now I will simplify by multiplying through. If I multiply through in the first bracket, what do I get? 2x to the 3/2 minus 6x. Okay, now I'm going to multiply these guys together. What do I get? Negative half. Now here I have to add exponents. I've got to be very careful how that happens. I've got a 2 and a negative half. What do you get when you add 2 to negative half? 3/2. Now observe what happened there. By doing the multiplying, we happen to create two terms that are now like terms. Which two terms are like terms? 2x to the 3/2 and negative half x to the 3/2. Those two terms can now be combined, right? What do we get? 2 take away half. What's that? 3/2. So we have 3/2 x to the 3/2 and then minus 6x. All right. So originally we took the radicals away. So now it's only good manners. Oh, just before I do that, extend the page again. And what I'm going to do here, I'm going to leave my denominator exactly as it is. This 2 right here, I'm going to write in this denominator. I'm going to factor out the 3 because there is a common factor of 3 with 6. And I can also factor out the x. If I factor out the x, what's left in the brackets? Well, here you took out x to the first power, so we have the square root of x left. Here, just a 2. Oh, I made one little mistake. Sorry. I made one mistake right here. In order to take out that 2 on the bottom, I needed to write this as a 12x. That's my mistake. That's better. Okay. So our 6 should be written as 12 over 2. That way you can take out the 2 and put it here. It has to be in both terms before you can take it out. Okay, so then this would make this a 4. That looks much better. A little bit of trickiness there, taking out that 2 from the bottom. All right. The last 3 questions are actually not bad. Okay, that was sort of the hardest one. That one was the hardest one. Okay. This one is actually really easy. Yes. Yes, you may. First of all, do the derivative. Every quotient rule derivative has this sort of template, right? Bracket, bracket, minus bracket, bracket over bracket squared. Just a matter of filling in the brackets now. The derivative of the top, 1. The bottom written down. The top written down. The derivative of the bottom. The bottom squared. Simplifying our derivative. Could you simplify the numerator for me? You should get just a number. Actually, you should get a negative number when you simplify that numerator. It should work out to -2. We're going to get the 3 x's canceling out, right? Because when you multiply through by the 3 here, you have -3x and +3x. Here you have a 4. Here you have a -6. So -2. I'm going to make a bold statement about this derivative. I want you to focus on this derivative. Focus on it. Are you looking at that derivative? Here's the statement. That derivative is always negative. Why is that true? It's true. Yes, Greg. Yes. So therefore, there are no tangents with what? Okay? So because the derivative is always positive, always negative, sorry, therefore, no positive tangent slopes. So there you go. That one's pretty easy. Number 5, also easy. Now, for some reason, they like to give you questions like this where one of the two functions is unknown. So you have a function that's composed of two functions, one of which is unknown, the other one is 4x squared. So can we still do the quotient rule when one of them's unknown? Yes. But the result is also unknown. And the reason is part of it will be unknown. All right, so do the derivative of the top, multiply by the bottom, subtract. Write down the bottom. Take the derivative no, just write down the top, sorry. Getting my order mixed up here. Write down the top and do the derivative of the bottom. And now we have 4x squared. Quantity squared. So on the bottom here, on the top, we can factor out an x squared. No, just an x and a 4. So we factor out a 4x. We have f prime of x times x. And then we have f of x times 2. On the bottom here, we have 4x quantity squared, giving us 16x to the 4th. And now, of course, we can cancel these two terms. The result is x f prime of x minus 2 f of x all over 4x cubed as our final answer. Okay, our last example is a tangent question, and sort of a tangent question with a twist. Although, where did it go? It's not on my thing, but it's in your book. Okay, I'll do it anyhow. I'll do it because it's in your book. She probably wants it done. All right, so number 6 we'll just put here. Okay, class. I have a serious question to ask you. If somebody asked you to quickly sketch x squared plus 3, could you? What would it look like? And in less than 10 seconds you could do it, right? Okay. Now this is a little bit different because usually they give you a point that's on the curve and ask you to find a tangent from that point. In this case, we're giving you a point that's not on the curve. You know what point we're giving you? The origin. And we're saying that there's two possible tangents, and I think you can see that there would be. There's going to be one that hits the curve like that, and one that hits the curve like that. Two possible tangents to this curve. And you know what? They don't tell you the point of tangency. So I guess I just better put a point like x there, because I don't know what it is. And for the y-coordinate, though, I could put y, but I have more information than that. I know my y-coordinate. I know what the formula is for my y-coordinate. It's x squared plus 3. So I could at least put that in there. Now, I'm going to find the slope two different ways, old-fashioned and new-fashioned. All right, so we're going to create a little equation where slope equals slope. Slope the old way, like Paul Bunyan and his ox, blue, and slope the new way like the chainsaw. I remember watching that cartoon when I was a kid. All right, so now the old-fashioned way looks like this. You'll recall this from Math 10, right? y2 minus y1, x2 minus x1. All right, except I'm going to use these points, right? They are both on the tangent line, so I can legitimately use them to find the slope of the tangent. All right, so what's my y2? It's x squared plus 3. What's my y1? It's 0. What's my x2? It's x. What's my x1? It's 0. Now, on the right side, I'm going to get the slope the new way, which is taking the derivative, right? What is the derivative for x squared plus 3? What's its derivative? 2x. So put that on the right side. These have to equal each other, don't they? What have I created? A monster? No. I've created an equation that I can use to solve for x. Oh, the mystery of it all. Now, I could just solve it, but I'd be robbing you of the thrill of discovery. So why don't you solve it and see what you get for x? And we'll compare notes in just a few seconds. I want this equation solved, people, by you right now. Let's do it. By the way, if you get an irrational answer, just leave it in root form. Okay? Leave it in root form. How many are sitting at looking at positive negative root 3? Positive negative root 3. Okay. That's exactly what you should have got here. If you cross multiply, you get x squared plus 3 equals 2x squared. You subtract x squared. You take the square root. As I was walking around, I saw that many people had remembered the positive negative. Good for you. And there are two possible tangents. One over here, right? And this one will have the negative x coordinate, right? So we do have two possible solutions. One of them is at root 3 comma something, and the other one is at negative root 3 comma something. How could I find the somethings? Plug into the original equation, so let's do that. And believe it or not, both of these y-coordinates are identical and rational. Yeah, even though x is irrational, which it can be at times, y is rational. So the y-coordinate, we simply just plug in the x-coordinate, right? We add 3. It's 6. How many are looking at 6 for both of those? Okay. And you can see it would be very easy now to find the tangent lines, wouldn't it? They didn't ask for the tangent lines, but it'd be so easy to find them. Okay? Okay, class, you have an assignment. It's on page 95. And the wise Math 31 student will do this assignment. Yes. We still have a generous amount, half an hour of class time. I don't normally give you that much. Half an hour of class time to get this assignment done. I promise you this. If you do the assignment, the quiz on Thursday will be much nicer, easier. Oh, why didn't you say quiz on Wednesday? Well, it's the Citadel. You're not here on Thursday? So that's it? That's it for us and Mr. Ashton, I guess. Okay. Thank you. Okay, if you didn't finish the quiz 3, the replacement quiz 3, you want to do that? Go ahead.
Can I give you my written quiz?
Sure. Thank you.